And you all might be thinking, what is cloud doing in Open RAN? The Open RAN runs on the cloud. So it's important that you know its performance before you deploy Open RAN on the cloud, right? So we're going to talk about that today. So what is NFV? What is SDN? What is cloud native? With the limited time, 30 minutes, I have squeezed many information and trying to make you understand what these technologies are and how it is helping, the telco, the telco operators to implement their telco network, right? So that's what we're going to talk about today. I'm the senior product specialist for CloudSure. The CloudSure is a tool which will test the cloud performance, cloud reliability and resiliency, and so on. So I'm not going to go more deep into CloudSure. The focus is to understand, the NFV, SDN, and cloud native, right? So the agenda today, we're going to start from the telco cloud journey. Where did they start and where they are today? So we're going to talk about that all the way till what is cloud native and Kubernetes. Right. So there are 8 topics. As I told, I have squeezed it. I'm going to complete this in 30 minutes. So we are also going to see end-to-end telco network. How does it look? And where is Open RAN cloud in the end-to-end telco network? What is NFV? What is SDN? SDN and NFV convergence. They work hand in hand. They work together. So how does that happen? We're going to talk about that. NFV will be obsolete very soon. They will stop using it. So why they're going to stop using it? We're going to talk about that. And the present and future will be cloud native and Kubernetes. So I will present a little bit on cloud native and an overview of Kubernetes, how it is going to help the operators to implement their cloud today using Kubernetes and cloud native. So we're going to start with topic 1 and 2, telco cloud journey and end-to-end telco network. So the telco cloud journey, if you see back in 90s, they used to deploy physical hardware. You might have seen the physical router, firewall. We are, in the new generation today over here. I don't know how many of you have seen the physical hardware. It used to get, just rack mounted, connect using cables, power it on, and configure individual physical hardware. That used to be in the late 90s. And very soon we saw that, in 2000, the operators, started deploying virtualization. That is, cloudification of their data center. So what, what did, what actually drove the operators to deploy virtual machines? We're going to talk about that in the next slide. And they started deploying virtual machines in their data centers. They started cloudification in the late 2000, the operators. But today, we are here. The operators are deploying microservices. I'm going to talk about that in the upcoming slides. It's all container-based applications. The one big fat virtual machine, it had multi-tier modules and made this one application. These 3 lines which you're seeing here is an example. So different modules of the application is packaged in one big fat VM. But in containers, they get split. So each module is an individual container, and that becomes a microservices. So they deploy the microservices. Why they do that? What is the benefit out of it? I will talk about it in the upcoming slides. And the containers, is getting installed on the Kubernetes cloud. The short name of the Kubernetes, we call it K8S. Between K and S, the full name of Kubernetes, there are 8 letters. So they call it K8s in short. So the containers get installed on the Kubernetes. It's microservices based application, and natively by nature, Kubernetes adopts and it gives you DevOps, gives you automation of managing the cloud and managing the applications inbuilt inside the Kubernetes. So it comes by default with DevOps. This is what is happening, and there are some important points over here. If you see, when you hear about 5G cloud, it is no more virtualization. It's no more VMs. There's no more virtual cloud. It is 5G cloud, which is running on Kubernetes. So we're going to hear only about Kubernetes going forward in the operator network. No more virtualization and the virtual cloud. There were cloud platforms built on OpenStack. There were cloud platforms from VMware. Of course, VMware also has Kubernetes today. VMware, vCenter, they are all virtualization cloud. So you won't hear them being used by the operators going forward. So it's all Kubernetes. And operator is the system integrator today. When the virtual machines and the cloudification started by the operator did not deploy that on his own. He did not configure the cloud on his own. He was dependent on the vendors. Vendors, for example, VMware, Nokia, Ericsson. So they were dependent on them, and they deployed the cloud. So vendor is, he's an expert with his own product. So it was kind of, he deployed his own cloud, and it was closed box. He was not allowing any other vendor to deploy the applications on the other vendor who has implemented the cloud. So it was like many vertical clouds inside the operator network. It was very hard to manage. But with Kubernetes, that is not which is going to happen now. So Kubernetes it allows one cloud platform, just one cloud platform, and any vendor application to run on Kubernetes. So therefore, now the operator is not dependent on any individual vendor. So he deploys the cloud, and he will ask the vendor to come and implement their application on the operator implemented Kubernetes cloud. So he becomes the system integrator now. So the legacy system integrators, we don't see them today in the operator network. And no vendor lock-in. It used to be vendor lock-in in the past. There was a cloud platform from a vendor, and the same vendor is also giving the application. Application, I mean to say, the VNFs. The VNFs was the old name in the telco network, virtual network function. So the network function is an application in the telco network. So they used to provide their own cloud. So it was a vendor lock-in. As I told, it was a closed box. Any other vendor application to be deployed on the cloud was not allowed. So it was a vendor lock-in. No vendor lock-in with Kubernetes now. So it's one flat Kubernetes platform, and there can be multi-vendor applications running on the Kubernetes cloud. A lot of in-house innovation. You might be aware of Rakuten, Reliance Jio in India, AT&T in America. Of course, other operators like in Japan, NTT, in Philippines also, Globe Telecom. So they all have in-house innovation because of they are deploying their own cloud. The operators deploying their own cloud. They have to manage that. They have multi-vendor applications to run on top of it. So there are a lot of innovations happening within their own in-house network that can be shared if something is very it has solved a very big problem. They can also share that innovation to the other operators or to the open source industry, which can be consumed by the other operators. So that is what is happening today. A lot of in-house innovations happening because they are deploying their own cloud. No more vendor lock-in. The old things are not there. So a lot of in-house innovations are happening inside. And yes, they've started to test their deployment because they are deploying their own cloud. So testing is important. Otherwise, they will not know whether the cloud is underperforming or the application is underperforming. So testing is very important, and they are following testing as part of the new 5G cloud, right? And the Kubernetes cloud, there are private Kubernetes cloud implementations from Red Hat OpenShift. VMware also has Kubernetes, as I told you. VMware Tanzu. It's deployed, on these private Kubernetes. There are other, Kubernetes platform from Rancher Labs, Robin.io. It can be anything, but these are some of the well-known, commercial brands. So hence I'm showing this, and this is open source Kubernetes. And there are also managed Kubernetes services from the cloud providers like AWS, Google, and Microsoft Azure. They also provide Kubernetes services, managed Kubernetes services to the operators, right? So this is about the journey of Telco Cloud. And yes, in the physical hardware, there was no requirement for the operator to test the performance because that was vendor's responsibility. But now, after, the applications, became cloudified, that is, virtualized and cloudified, and now it is microservices, the performance of the cloud or the performance of the application is important. It remains here also. So it has to be tested. So end-to-end telco network, over here you're seeing the radio, the front hall. Here is where the ORAN, the Open RAN cloud, that's the first cloud, which you would see in the telco end-to-end network. And then there is edge clouds for different use cases, for gaming, for V2X. V2X is vehicle-to-vehicle communication. You're seeing, self-driving car and all those things. That's all, managed by the cloud, by the applications installed in the edge cloud. And then there is a core cloud. This is where the user gets authenticated. He's going to get the 5G services from here. So, and then you have a backhaul. So these are different parts of the end-to-end network: front haul, the mid haul, cloud RAN, the backhaul and transport network, and the core cloud. This can be 4G. Even 4G can exist. Right now, there is 4G network also. It's not fully 5G everywhere. So 4G is also existing together. But one fine day, 4G will go away. The 4G cloud, you will not see that. And yes, this is, this is all cloud native and Kubernetes today. Even the Open RAN applications are container applications. So they get deployed on the Kubernetes cloud. So the BBU units, maybe Deepak is going to talk about that. That is virtualized and it runs on the Kubernetes cloud. And end-to-end, each of these domains are the testing domain. Spirent offers, testing in all these areas: the front haul, radio, the cloud, the applications. We have multiple different tools. My focus is on the cloud, and we test the cloud, the performance, the reliability, and so on. Right? And what is NFV? We are in the third topic. NFV is network functions virtualization. Right. So what happened was back in 2000, the physical hardware box, what the vendors did was, in order to utilize the benefits of cloudification, they extracted the application from the hardware. And hardware was just taken out. They extracted the application and they virtualized that. They made it a VM, virtualized application, which gets deployed on the COTS server, COTS, common off-the-shelf hardware. So it was a it was a server, like, it can be from HP, it can be from Dell, these COTS servers is what you see in the data center. Now that's getting used to implement the virtual applications of the telco. That can be container applications or the VMs, the virtual applications. So this separation of application and hardware is called as the NFV, Network Functions Virtualization. So that's all. This is all about NFV. So they started leveraging the cloudification, the benefits of cloudification, in the NFV. What are the benefits of cloudification? Let's say if you need to, upgrade this hardware, it was difficult. You wanted a downtime if you want to upgrade the hardware in the production network. But with virtualization, you can have a replica copy of it, and then you upgrade one at a time, and you actually don't need a downtime. This is the benefit of cloudification. So the operators, the telco operators, started to leverage these benefits by following this path of virtualizing their applications and deploying it on the cloud hardware, the COTS hardware, right? So which used many different components, like a fast storage, a fast networking, using DPDK and SRIOV NIC cards, which accelerated network forwarding and gave the same performance which physical hardware used to give. Physical hardware, it used to give line rate 10 Gbps or 40 Gbps throughput from one single hardware. Now that was difficult to obtain the same performance in the virtualization, but with the help of SRIOV and DPDK acceleration, data path development kit, that is DPDK, the network forwarding was accelerated, and they started to see the same performance what they used to see in the physical hardware. So HC is European telephony standards. They defined standards for NFV. This is a little complex, what you're seeing here. So in order to simplify that, so I have marked the areas. So this area is NFVI. I stands for infrastructure. The infrastructure where the applications runs on top of it. But this area is VIM, Virtual Infrastructure Manager. Now, what is the role of this VIM? This VIM is a controller. He is going to manage the lifecycle management of the NFV infrastructure. So he's the cloud manager, he's the cloud controller. So he's going to manage the cloud. He has given a name, Virtual Infrastructure Manager. At the back, if you see here, Virtual Infrastructure Manager is the VIM. So there are different reference points, how they integrate and all. So if a vendor, builds his VIM, so he has to, follow the HC standard. So he should, follow the ORVI standard so that he can get integrated to the other components of this end-to-end NFV architecture. So these are all the different reference points: V, VNFM, EM, and so on. So you can find more details if you go to the HC website and look for HC ISG standard NFV architecture. You would see this picture, and there's a lot of explanation there of what these SOL standards are, the SOL standards, what they are meant for. It's all very well explained there. So that defines the interoperability, the SOL standards. And there is one more area which is called MANO. These are managed network orchestration. So there are two components, NFV orchestrator and VNF manager, which will manage how the applications gets deployed on the cloud and how they get kind of upgraded, scaling, and so on. So here is where the applications gets deployed and runs on the infrastructure. So these are the 4 areas of the HC NFV. So if somebody is talking about NFV infrastructure, what it is. If somebody's talking about Mano, you know what it is. So that's why I had to show you this picture. And now, let's talk about what is SDN and how would SDN and NFV converge together. They work hand in hand. So the SDN is the same concept like NFV. The applications get, extracted out from the hardware. In the SDN architecture, what happened was all the network functions, the control plane got, extracted from the hardware, and the control plane and data plane got separated. And then you have that is SDN controller. This is SDN controller. This is the control plane. And the hardware is dummy. There's nothing on this hardware. It cannot take any decision. And this is one big, switch or a router for this SDN controller. You may have hundreds of switches. You may have thousands of switches or thousands of routers. That all, appears to the SDN controller as one big switch or one big, router. That is, because they extracted the control plane and they separated the control plane and data plane. Control plane moved into the SDN controller, and data plane became, dummy. It has no intelligence. It just remains there. It's simply a fabric, which gives you a raw bandwidth to forward the traffic. An SDN controller takes a decision how to forward the traffic. So when he takes a decision, he's going to program the data plane using OpenFlow. It has a lot of policies in OpenFlow based on the mapping. Back in OpenFlow in 2016, 2017, they had 12 tuple matching. 12 tuple matching means 12 different kind of source. It can be MAC address, it can be IP address, it can be a switch port. That's the source, and destination where to go, another port or another IP address. That's all programmed by OpenFlow. It's called southbound protocol. OpenFlow is not the only southbound protocol. There are different protocols to program the data plane. It can be netconf, it can be OVSDB, BGPLS, and so on. There are multiple different southbound protocols. There are custom APIs as well to program the data plane hardware, the switch or the router or the firewall. This can be anything. If you see SD-WAN, it works in the same concept. So this can be router, firewall, DDoS, and so on, different underlying hardware. And on the northbound is where it gets integrated to the cloud. OpenStack you're seeing here, it means it is integrating to the NFV. So there's a ML2 plugin on the OpenStack. That's where the SDN will get kind of integrated. Right? And also it can give access to the customer or the administrator to configure the SDN controller. It can be automated or it can be manually configured. It depends on how you manage that on the northbound. So you have a REST API integration towards the northbound, which allows you to configure automatically or manually. And the other interface is getting integrated to the NFV on the ML2 plugin of the OpenStack, and it allows the NFV to program SDN. And SDN, the benefits over here, if you see, there is an SDN controller and SDN capable switch. This is programmed by OpenFlow. So let's say you create a VM and the SDN automatically creates the port on the vSwitch. vSwitch is a virtual switch inside the server connecting the virtual machines. So it programs the vSwitch port. It may be which VLAN, what kind of firewalling that it has to do, MAC filtering and QoS, the quality of service. So those policies gets implemented on this port and it programs automatically. You don't have to manually configure the vSwitch. The configuration is here in the SDN controller. And on the southbound, it uses OpenFlow or any other protocol like netconf or a custom API to program this switch. And this switch, this green line which you are seeing, is the SDN controller controlling the switches. It's controlling the hardware switch. It's also controlling the V switch. It programs the switch. Now, the other benefit, what happens is the cloud can move the VM from one server to another server. That is, the OpenStack. OpenStack, the cloud controller, he takes out the VM and he will deploy it here on the other VM. Sorry, on the other server. Why they do that? Maybe they need to upgrade the server. They need to do some maintenance on the server. So they move the VM from one server to another server. When they do that, SDN controller knows about it. He moves the configuration also onto the new server. You don't have to worry that I have to pre-configure this before I move the VM to the other server. SDN controller takes care of that. He moves the configuration also on the physical switch and also on the virtual switch. He does that. Right? And how do they converge? In an isolated schedule, they first deploy NFV. In an isolated network, they would deploy the SDN. They're going to test here. They go phase by phase. And at one point of time, when they completely cloudify their network, the operator network, SDN and NFV will come together. You saw NFV is cloudifying the applications, and SDN is allowing you to manage the networking. We just saw the networking over here. You move the VM, cloud is moving the VM, SDN is taking control of the movement of the configuration also. Movement of the network configuration. So the network configuration appears here on the new location where the VM is moved. So that's taken care, at one point of time. So SDN and NFV will converge together and they work hand in hand together. Why is NFV obsolete? Why operators are stopping to use, the virtualization, the NFV, the virtualization? Excuse me. So we're going to talk about that here now. So the VM, the virtualization, the application straight away came and it got, virtualized. It became a VM. If you see how that all works, so you have the server. On the server, you will install the hypervisor. It's nothing but the Linux operating system, which has the capability of virtualization. So that we call it as hypervisor, libvirt and so on. It allows to run VMs. So it's not a simple Linux. You install Ubuntu Linux. You can't expect, it is hypervisor ready and you can install the VM. There are certain components that you will have to install. For example, apt install, the libvirt, and so on. That will enable virtualization. Libvirt install KVM. So KVM is one more component which makes hypervisor ready. The Linux is hypervisor ready. Then it will allow you to install the VM. So just focus on this green box. There is, one more, there is an application, VM, but that VM is not, alone. That VM comes with a guest operating system. It's an overhead. You already have a Linux operating system, Ubuntu, and this VM is also having the guest operating system. Application cannot run on its own. It needs operating system. So it has, the Linux operating system on top of the application. So this is one big fat VM. It has a dependency of the guest operating system. So when a VM boots, it's going to take sweet 4-5 minutes on its own time. It takes, its own sweet time to boot. It takes, 4 to 5 minutes. First, it has to boot this guest operating system, and then the application is available in the network. It's very slow, and that's not, today's cloud, and they cannot, leverage this, these VMs. If they have to be fast, if they have to be, the 5G cloud, the 5G cloud is very fast. Something happens, recover soon. What do I mean by recover soon? If you see here, the VM to boot, it takes 4 to 5 minutes. It cannot recover soon. And hence, the operators have decided to stop using VMs, and they want to follow the containerization, the container networking. So what happens here, this one application has multiple modules. It may have 4 or 5 modules. Those individual modules get distributed as containers, multiple different containers, and they get installed on the Kubernetes-based infrastructure. This is a lightweight application. It has no dependency of the guest operating system. It's as good as installing applications on your phone. You install the applications on your phone, and whenever you don't want it, you will delete that. It's the same concept here in the containers, and there is no dependency of the guest operating system. This is one reason where the operators are deciding to move away from NFV and follow cloud native. So cloud native is nothing but containers and Kubernetes. Microservices, if you see this application, this was all one big VM earlier. But today, if you see, it's all separated into multiple different applications, different containers. It has a load balancer, it has a database, service mesh. They are all different containers, and this is microservices and gets installed on the cloud. This can run on one server, this can run on the other server. It's so I could say so flexible. It can be installed anywhere inside the cloud. It's not one big VM. Earlier, it was one big VM, but now it's split into different container applications and runs on the infrastructure. So this is about this is the reason they are moving away from NFV into cloud native and Kubernetes. So what is cloud native? So cloud native is the old NFV. We saw the NFV infra, the Vim, the Mano, and the VNF. This was the HCNFV architecture. But the cloud native, virtualization versus containerization. You could relate to the same architecture, but these controllers, the orchestrator, NFVO, VNF manager, and the Vim is now Kubernetes. So Kubernetes is going to manage the cloud, and the Kubernetes is also going to manage the application. Just watch the names. Here it is VNF, virtual network function. Here it is CNF, container network function. All microservices application. Here it was big fat VM. Here it is microservices. It's small, very flexible, and very modular here versus one big fat VM here. So this is Kubernetes and cloud native. Cloud native is simply Kubernetes is not cloud native. Kubernetes is part of cloud native. Cloud native is if you go to CNCF, cloud native network foundation, look for landscape, search for CNCF landscape in Google. It will give you this big picture. Where is Kubernetes here? This is cloud native. This full thing is cloud native. Kubernetes is here, who is the container orchestration. Container orchestration is Kubernetes. That's all. He's the cloud orchestrator, cloud controller. That's all. There are many other components which makes cloud native. Which makes it faster deployment, automated deployment. If something happens, heal automatically. Something fails, it has to heal. It has to heal automatically. So all these different components makes cloud native. There is cloud native storage. If you see here, that's nothing to do with Kubernetes. Kubernetes can control the cloud native storage, but there are different components. And just remember networking also. There are different types of networking. There is CNI. CNI is cloud native interface, which connects different container applications within the microservices together. CNI is a policy enforcer. He will say from one container to another container, how does it communicate? Do I have to implement firewall policy between one container to another container? So all that policy enforcement happens in CNI. That's the cloud native network. So Kubernetes alone is not cloud native. cloud native, there are so many other components. You can learn about this, all about the cloud native, all these individual components in CNCF landscape. So I ask you to read this after this training session. This is from one of our operator. When he was deploying, you see the container orchestration, Kubernetes. He was trying to choose Red Hat or Robin or Amazon. Amazon offers the managed Kubernetes, EKS, that is container orchestration. Cloud native networking, what type of networking to take, what type of storage to take. This and all these 19 different components makes it an end-to-end cloud native network. So cloud native, if you hear cloud native, it is just not Kubernetes. Kubernetes is only the container orchestration. So there are different components which makes the cloud native network. And this is what you will see going forward. This is the present and future of the telco network. This is my last slide overview of Kubernetes. So in Kubernetes, what is Kubernetes? So there are some fingertips, that you have to memorize, right? So Kubernetes works in master and worker node relationship. So all the configuration is done here, and that configuration is implemented in the worker node. So again, control plane, data plane concept. So this is the control plane and this is the data plane. So there is nothing, this is not application perspective control plane, data plane, but it's just a relationship, the way the Kubernetes cloud is managed. So there is a master node, which has different components over here, which is controlling the worker nodes, which is managing the worker nodes. This is where we deploy the CNFs. There are different components here. We talk to the API server to configure the Kubernetes. So I need to create a container application. So I'm talking to the API server. I send the commands here, and API server takes care of deploying that container application on the worker node. So there are clusters in Kubernetes. We use that language, cluster. So what is a cluster? Cluster may have a group of 10 servers. There may be another cluster, a group of 100 servers. Cluster 2. There may be cluster 3, which may have 500 servers. So there can be any number of servers within a cluster, and there can be any number of clusters for the Kubernetes master. So that's the way it works. And API server talks to the kubelet, and that takes care of deploying the container applications and so on. There's so many things which you could learn when you Google it, right? One more important component is the controller manager. So what it does is, I like this, in Kubernetes. So in Kubernetes, you say the container application must have 2 replicas. So it's not one application. That application will have a mirror copy, a replica copy for reliability or for resiliency. So one of them fails, what this controller manager will do is he's going to monitor that, observe, act, and analyze. So he's going to observe, he's going to monitor for this particular application. Do I have 2 container images, 2 container applications? One fails, the other one will take over. So that is for resiliency. But what Kubernetes will do, what will the controller manager will do is, if one of them fails, it will recover them. It will heal them automatically. That's the beauty of the controller manager, the control manager. So desired state is equal to current state. My desired state, I intend that my application should run always with 2 container instances. And Kubernetes ensures that it always runs 2 container instances. If it fails, controller will monitor that and it will bring back the failed container application. So desired state is always current state. At any given point of time, desired state is equal to the current state. And that is taken care by Kubernetes. It promises that, and it will do that. Kubernetes networking is something which you all should know. When I started learning Kubernetes, I found the networking was very complex, but now I have found it's very easy. So there are when you deploy a container application, it also deploys the service. Service meaning when you deploy a VM, it's directly available over an IP address. I take a SSH control of the VM, or I take a web interface, a web GUI access to that VM. It is not going to work that way in containers. You deploy a container in Kubernetes language, we call it pod. Pod can have multiple containers within the pod. Even a single container is a pod. When you deploy a pod, there is a service also getting deployed. And that we talk to that service. We don't talk to the pod directly. So service is a kind of a proxy. We hit the service, and service will take care of distributing the traffic to multiple different containers at the backend. So it also creates a service. You install an application, you get a manifest file to deploy the application. So the application alone does not get deployed. It also gets deployed with the service, and the service gets exposed. And we communicate to the service IP, not to the pod. Cluster IP, ingress, load balancer, and node port. There are 4 different types of networking. Anything, there is something called north-south communication. It means that the end users accessing their applications installed inside the cloud, that is called north-south communication. For all the north-south communication, we can use ingress type of networking configuration, or we can use load balancer type of configuration, or node port type of configuration. They all work similar. The benefit of using load balancer, it allows us to use third-party load balancers. Kubernetes also offers load balancer. There are third-party load balancers from MetalLB, Red Hat. What is that? You have F5, Radware. So there are different, load balancer vendors. We can use that third-party load balancer. So that flexibility you get when you go with this kind of service. So all north-south communication happens on these 3 types, any of these 3 types of networking. Cluster IP is container-to-container communication, that is pod-to-pod communication, goes through cluster IP services. Pod-to-pod also do not communicate directly. It's not direct. It will go through the cluster IP service. So that's the rule, and that is how it works in Kubernetes. So when you see cluster IP, it is east-west communication. It's not north-south communication like ingress load balancer or node port. So this is east-west communication. Pod-to-pod communication is on cluster IP. User-to-pod communication is through ingress, load balancer, or node port. It's very rare. I have not seen, at least in all my experience, I have not seen pod-to-pod communication is over an IP. No, it is through a service. It can be HTTP port number 80, port number 8080, port number 8989, whatever the service port exposes, it will communicate on that particular port. Same thing on ingress, load balancer, and node port. And this I have already talked about it. There are different platforms, different flavors of Kubernetes. There is, from Red Hat, OpenShift, you have VMware Tanzu, and you also have, managed Kubernetes services from the cloud providers. So this is all about Kubernetes. And what, CloudSure will do, that is parent tool. We used to test the virtualization. We are not testing this anymore because the operators are stopping the NFV. They are stopping the virtualization. So we are not testing this. We test, the Kubernetes infrastructure, the compute network, CNI. We test the CNI as well, and the storage. Example, Red Hat OpenShift. And on the application layer, we test the resiliency and scalability. What is the resiliency if the application fails? Is it self-healing? Is the Kubernetes self-healing it? We have seen instances that the CNF, which runs on the Kubernetes, was incompatible with a particular Kubernetes platform. It may work on Red Hat OpenShift, but it may not work on Amazon EKS. So that interoperability is what we will validate in the CNF resiliency and CNF scalability. On the application layer, we test these methodologies, and we also test the Kubernetes infrastructure for performance, for stability, so that there are no anomalies, and you can successfully deploy it in the production network. Yeah, so this is all from my side. Thank you very much. I think I have extended 15 minutes. I'm really sorry for that.
Okay, so good morning, everybody. Next 30 minutes, probably I'm going to take of your time. And during this time, these next 30 minutes, I'm going to talk about the kind of challenges that operators are facing in ORAN. There are a couple of market trends with the use cases that customers are interested to understand how they can achieve the real world performance with new ecosystem called ORAN. And definitely there are a lot of innovation happening in ORAN field from RAN, especially on the RAN side. So we have seen virtualization and cloud-based applications in the core. This is, I would say, with the ORAN, you would see a lot of innovation towards RAN, which is definitely for good, greater good, and it would bring a lot of competition. So probably we'll talk about market trends and the kind of solutions that Spirent is offering to help most of our customers with benchmarking, validating the device features, understanding how good your performance is for your device, compared to the requirement that is defined by standard. But at the same time, there would be carrier requirements that they wanted to validate ORAN with a specific set of requirements from their side. Could be quality of experience, with better quality of experience, definitely. So let's understand the objective of Open RAN. Definitely, it is to increase the competition across different vendor ecosystem. So not relying on few vendors, right, for their deployment. So operator can choose, right? They can make a la carte, have different vendors in their entire network ecosystem, rather than relying and being limited to certain few numbers of vendors, and that would definitely freeze lot of uh, development and innovation from operator side, because it's a vendor lock ecosystem. So to avoid that, they wanted to have an open network architecture where standard are there are interfaces which are standard driven and more open towards so that there could be many number of vendors who can participate, and definitely the ecosystem which is software defined, based on software defined architecture. Then increasing the innovation with lot of intelligence, AI, ML, because a lot of data is flowing. We are talking about uh, terabytes of data, with 5G growing with 100 megahertz to probably carrier aggregation supporting multiple carriers and moving towards 6G. We need a path where higher data demands and intelligence can be accommodated in the network requirement, and definitely bringing that innovation towards RAN, because RAN has been way complex than and limited to few numbers of vendors. And then new service models, like I said, there is a we are talking about Chat GPT now, right? So definitely the innovation is needed where we can integrate machine learning, artificial intelligence to the network, and there has to be optimization which is not uh, that has to be a system self-learning and optimizing the network based on customer requirement, based on users quality of service, based on their applications. And we are going to talk about some of the key use cases that RIC, which is a part of Open RAN, and especially driving intelligence based on AI and ML. we are going to cover few use cases based on that. So new service model, which is disaggregated and virtualized, and bringing the flexibility in the deployment, and they're leveraging the cloud native principles that has been deployed already in the core side. So that is what we are going to see ORAN bringing with a new lot of newness in the network. So talking about market trend and key challenges, first is definitely now the expectation is set, but at the same time, what we see that lot of vendors are there who are working on RU, DU, CU. We are going to talk about the architecture, but I'm just referring that why now this is a challenge, right? Giving the same piece of the job to multiple people definitely will bring new complexities and challenges, and that's where there's a need of validating end-to-end multi-vendor environment and ecosystem to ensure that it works properly, it works with other vendors, and it comply to the interface that standard has defined. And then there is another challenge is related to budget, which is pricing. So ORAN is promising to drive competition-based network, which is more affordable to carriers, and at the same time, it is uh, solving this problem where operator used to spend a lot of capex, a lot of money on capex and opex. And last and not the least is definitely making sure and assuring the performance that we have been promising in the standard documents, right? 3GPP has been talking about 5G achieving high high peak data throughput, and are we able to achieve that kind of data throughput, right? And assuring the promise is definitely the key requirement. Especially it could be ORAN specific standard requirement, or it has to be carrier specific requirement, because each carrier has different set of challenges and they have different set of combinations in the network deployment. Especially, let's say there's a deployment on FDD or TDD, then there's a deployment based on the frequency band. Somebody is deploying in 700 megahertz or 800 megahertz, and then you would see 2.3 gigahertz, 3.4 to 4.2 gigahertz. So there is a wide range of spectrum that we are seeing that these services are being deployed in, right? So there is a FR1 range, which is up to 6 gigahertz. Then we are also seeing FR2 now, right? We are talking about the ecosystem where we carrier can deploy services on millimeter waves also, right? 24 gigahertz, 42 gigahertz, sorry, 39 gigahertz, and then 52 gigahertz. We are also seeing some of the like new releases, probably release 18 talks about higher range of frequency to enable wave based applications. So there has been a lot of uh, complexities in terms of radio deployment already, and then on top of it we are talking about Open RAN in 5G. So this is definitely has to be tested for its performance and robustness. So why there is a need of testing? So we have seen in the early R&D there is a pre-silicon conformance test requirement, which is basically testing as per probably standard bodies like 3GPP or ORAN, defining the test requirements, and we are just validating, matching whether, saying yes or no, and providing the benchmarking to NEMs. But that's not enough, right? We are talking about the advanced application. There's a multi-vendor ecosystem. There is a performance which is based on standard bodies, but at the same time, when we go out in the field, we have to see what kind of voice quality user is getting, what is the video, how video applications are working, right? There are a lot of streaming based application. There is a lot of high definition gaming applications are there. There is a lot of like like applications like OTT platforms like WhatsApp or Skype, or which are work like generating a lot of data, and then it has to be tested for like in real time field based performance testing. So let's talk about Open RAN architecture. We have seen Open RAN being splitted in RU, DU, CU, radio unit, distribution unit, and centralized unit. So whatever G node B, we have seen, if you remember the 4G and 5G architecture, whatever G node B or E node B used to do, now we are splitting that in 3 different functionalities called RU, DU, and CU. I have this next slide where it exactly says what functionality has been broken down into multiple pieces. So if you see from our left hand side, there is a traditional black box approach, which was like, this is the protocol stack for G node B, providing services from RF to SDAP applications. Now this has been splitted to ORU, ODU, OCU, and if you see ORU, it's probably just the lo-fi and supporting only the RF conversion to IQ packets, and then supporting some real-time processing, which is near the site and integrated probably with the antenna, or it could be separately also. Then we have ODU, which is having the high physical layer along with MAC and RLC. And then we have control plane OCU and user plane OCU, where we have PDCP, RRC, and PDCP and SDAP. And the new architecture which has been evolved is RIC, near non-real-time RIC and near real-time RIC. And this is kind of brain of this architecture. So CU, what you see from the CU side, it performs less sensitive processing, but is still very critical because it's a part with ODU, right? So based on the split that operator is choosing, option 2 or 7.2x, the configuration we have seen is that ORU, and then we have ODU and OCU combination. Then there is a RIC, and then we have the core. So in this scenario, probably CU is talking to multiple other CUs and probably hundreds and thousands of DU and millions of users in that case. And if we see further how this how these architecture is going to help processing real-time applications and non-real-time applications, I'm going to cover a few more slides on that. So if we see there is a time-sensitive applications where real-time processing is required, and that's where ODU is having hi-fi, and you see from coding to IQ compression, there are like lot of processing is dependent based on the channel conditions, like how good the radio condition is, right? Based on the user location from the network and based on the network conditions, you will get probably the modulations from poor to good. And so your mobility will be affected, your application quality will be affected. Then there is a low time sensitive applications where probably number of users or analyzing the traffic volume, and that would be taken care by upper layers of ODU and OCU. So moreover, what we see that beamforming related, right? We are talking about in the era of massive MIMO, right? There is a term called massive MIMO, and we have seen a significant growth in number of antennas being used for transmission and reception of the signal. So on the user side, right, in most of our mobile devices, we might have 2 antenna, but 5G, most of the device might be having 4 antenna, and in future probably 8 antenna. Definitely number of antenna will increase the size of device, and that's why there is a need of higher frequency to reduce the size of device. So mmWave will address that challenge. And talking about massive MIMO, on the G node B side, we have seen that now with Open RAN, there is a deployment happening for like all variety of configurations, like starting with 4x4, which is small cell or femtocells, and then moving towards macro, and it could go as maximum as like 16, 32, and 64 antenna RF ports for TXRX. So there is up to like 128 antenna elements which are being used for uh, like 64 for transmission and 64 for reception. So that kind of configuration is definitely bringing more complexity, and then it has to be tested for beam forming scenario, because beam forming is very critical and essential for mesh MIMO design, and that's where new set of complexities would be added further. And I'm going to talk about like how Spirent is helping this with addressing overall challenges from end to end. So let's just understand, having a different nodes and component in the network, we need to test each node for its own set of challenges, and then end to end. So on the device side, like I do only care how good my voice quality is, how good my applications are working or performing over this network, right? No matter who is the carrier or how it is being deployed, the end-to-end performance matters to me a lot, right? Whether mobility is happening seamlessly, there is no handover failure, I'm not dropping the calls, and that's where the end-to-end performance is needed, along with field optimization, because there is a continuous learning that will be happening from the field, and same has to be reflected in the network. And if we talk about RU, there is a need of conformance testing to validate how the radio is as per the standard requirement 38.141. There's a standard document talks about validating the radio for its conformance test requirement. And then there is a need of functional and performance, where you can validate functionality and do the real-time field application testing, probably testing uh, the antenna performance, or do testing beamforming, like I said, validating the different frequency deployment. So as a NEM, they have to support multiple bands on the same G-Node B, and then it has to be tested for different set of combinations, frequency, bandwidth, number of antenna involved in the TXRX, and so on, including the quality of service. And then the front hall interface, which has to be tested. It's a eCPLI interface, and there is a need of testing for, again, interoperability, synchronization, and there is a DU and then CU. We both are sitting on cloud-based network, right? And one of the slide talks about that DU and CU is sitting in cloud as network, and probably CU or core could be in regional cloud. And based on how the operator is choosing the deployment model, the test requirement becomes critical. And then CU supporting lot of traffic, like hundreds of DU and thousands of RU and millions of user, then there's a need of testing the performance of CU along with the scalability. And then integration, right? We have to support different type of vendor from RU, DU, or CU or core, any component from this network. With the openness we talk about in Open RAN, the different vendors jointly working to provide a complete network, and then it has to be tested for its performance along with the security, right? Security being very critical when we are talking about so many different hardware and software combinations for providing complete network. So Spirent, right? We provide testing where we can isolate, or we can provide just the emulation for the rest of the entities except the device under test. Let's say in some scenario where DU and CU is device under test, we can emulate RU, we can emulate the traffic number of users, we can emulate the core, and we can provide the complete testing. Moving on, if CU, let's say, is on the device under test, then we have to also emulate DU. Let's say if somebody wanted to do CU along with the core, right? They have their own design for CU and they have their core or some of the core component. Aspirant will emulate the rest, or vice versa for in case of combination of RU and DU, depends on the vendor. Like there could be any of this requirement that I have just talked about. And for, let's say, just RU vendor, they wanted to do the wraparound testing. And in that case, including DU, everything has to be emulated along with eCPRI support and the RF support, both sides. So what Aspirant is bringing from a uniqueness perspective and compared to our competition in the market, we have a single interface, right? We talk about emulating lot of component in the network. In, like, let's say, for example, if you wanted to test RU, then DU, CU, core, all the core component like AMF, UPF, and all the 5GC component has to be emulated along with the UE. And then on top of it, applications running FTP, UDP type of traffic, and then providing the quality of experience measurement. And all of this, right, in the past has been operated with different UI, different solutions altogether. Now, today also, we are using multiple solutions to address all of these problems, but with under one umbrella, right? So there is a single user interface connecting all the dots for configuring, for allowing configuration, creating test cases from a single user interface, and along with the automation, right? Whatever automation you're bringing. So we support open APIs, and there is already a set of automation given with the single user interface to our customer with predefined test cases from ORAN and from 3GPP. And there's a like big list of test cases based on the device under test, like RU or DU or CU. And this all supported for providing real world performance, for providing multi-vendor interoperability, supporting standards requirement. And this is one of the example where we can see how single interface is controlling UE emulation, controlling channel conditions. So I was talking about that how we are bringing the real world performance and evaluating the RF performance. And the channel emulator basically brings the real world conditions in the lab. It will emulate the delay, it will emulate the environmental properties like multipath and speed. So you don't need to go for actual drive test. You can basically test your handset in the lab if you have Vertex, with providing like very varied channel conditions, impacting around 20 to 25 different KPIs, which you can evaluate the RF performance of your device with. And in this scenario, we have, let's say, RU, DU, CU as a system under test. Then we will be emulating rest of the interfaces N1 to N3, S1, X2, XN for CU handover. And then we will be emulating rest of the core components, including the PDN or IP connectivity. Now, UE emulation is okay, but is that enough? Are we able to test the real 5G commercial device? So while we know that there are a lot more devices are available supporting 5G interface already, I'm sure that I would be interested to evaluate the performance not over an emulated network, but with a real device handset, right? So that's also Aspirant is supporting today. And we can actually connect a 5G handset. Instead of UE emulation, we can have a real 5G device and we can evaluate the performance. To test what? So we can test isolation, like nodes in isolation, where let's say RU, DU, CU, and RIG. Any of these component could be device under test, and rest of the left and right hand side devices would be emulated by Aspirant. Could be a combination like adjacent where RU, DU, or DU, CU, a set of different network entity could be tested altogether, and rest of the required entities would be emulated by us, or it could be end-to-end, right? Probably you will be having RU, DU, CU, and even core from your side. We would be providing probably UE emulation and the automation for like automating the entire infrastructure, helping you to build the test cases as per customer requirement, like as per carrier requirement or standard requirement. And this would definitely help in solving lot of interoperability issues. You can have different vendor ecosystem to test end-to-end performance. Let's talk about RU test solution. So if let's say RU is device under test, what I need is to definitely test the RF performance on the left hand side, and at the same time to test the front hall performance, which is based on eCPRI. So what we are doing in that case, we are emulating RF channel conditions using our Vertex channel emulator. We are providing the RF interface here. It could be conducted environment, it could be OT environment, depends on what you are testing. If it is a sub 6 gigahertz ecosystem, then you don't need OTA test environment. It's quite easy, just connect the RF cable to your device. Now it could be UE devices, real device, commercial device based on Samsung, Qualcomm, or any chipset, any other chipset, or it could be emulated emulation, right? Device emulation, where you wanted to stress the network by providing the scale like 128 users or 256 users or higher number of users, just to see how your DU is going to perform or how your RU is going to perform. And then if you have like multiple devices connected to this system, at the same time you can test your RU for its beamforming testing or capabilities. On the right hand side, we are providing the OFH emulation, like where we can take this eCPRI packets and process it further towards core. So we will be also providing ODU emulation, then core emulation and application support, and then on top of it, a single user interface with complete automation. So what do you get when ORU is under test? Basically, we will be able to provide you 7.2 split for testing conformance, performance, functional testing. And as of today, we support LT ODU as well as NR ODU, and it's complied with eCPRI interface 7.2x interface, supporting 10 gig as of today, and in future it would be supporting 25 gig interface. And we are supporting complete range of FR1, which is 400 megahertz to 6 gigahertz. So regardless of which region you belong to, what different bands your device supports, you will be able to test with the same solution. Now, for MIMO layers, we support as of today 2x2 on the RU side. And in roadmap, we have 4x4 capabilities supporting TDD and FDD both. Talking about ODU test solution, so in this case, we are just reversing and we have the device under test ODU. Now, if we see the previous picture, we need RU emulation right now. And on the right hand side, we need CU and core. And that's exactly what we have here. So we have RF channel emulator, which is working on RF, and then it is converting those packets to IQ data. So there is a baseband synchronizer, which is converting your RF to eCPRI packets. And we would be able to support 10 gig of traffic right now. And you can do all sort of testing, whatever we have shown on RU side. Just adding more to it, that it would also, like, we allow you to play with combinations of like supporting multiple CU or multiple RU. Right now, multiple CU is supported as of today with our solution. Multiple RU is our roadmap. As of today, only one RU is supported. So, and if we are like taking the UE emulation, we are able to support as of today up to 256 UEs, generating up to 25 gig of traffic. And at the same time, it would be allowing you to do handover, wraparound, all sort of testing, where you can test high capacity, scalability, and the real world performance, bringing the real field data probably, and while you're doing the drive test, capture the data, play it back. That also is supported today on our platform. End-to-end system, where RU, DU, CU is the device under test. Then rest of the entities supported with single user interface, providing you the similar capabilities. But now there is a preset of library also included based on the device under test. So there are test cases which are related to security. There are test cases where uh, like we have combinations of ODU, OCU with different scale, and it would be tested with a rich library. So we support channel models as of today, defined by standard, but at the same time, we can also recreate channel models using our advanced application called Advanced Channel Modeling Tool. And it would allow you to test 3D beamforming and advanced antenna system for your end-to-end test requirement. So it's the same concept. I would skip the slide just to keep the time. Yeah, so if let's say CU is device under test, we can emulate up to 2048 DU, right? Like I said, CU is something where a lot of traffic is combining from like thousands of RUs, hundreds of DU, and millions of subscribers. Now we can support up to 2 million of users on the UE side, like emulating up to 2 million users and generating up to 100 gig of traffic on OCU level. And that's what is needed if you really wanted to stress out your complete end-to-end network. But at the same time, you would be able to test all the applications like voice, data, handovers, and scale, probably VONR, Volte applications, and handover, uh, checking VONR call, whether it's the handover is happening properly or not. So all sort of scenario can be created, use cases created, and there is a huge list of pre-built library available with our solution already. Rig test solutions, or Rig is kind of brain that we have seen in the ORAN ecosystem. Now we have seen a lot of XF and RF application, like which are based on near real time and non-real time uh, part of the rig. So some of the use cases that I have seen and I have read about is like providing the resources, RF radio resources based on QoS requirement of the user, doing advanced traffic steering, right? Based on the traffic, it would steer the signal strength, and it would increase uh, the network focus towards that particular traffic to address the congestion. Then, because we are using massive MIMO, there is a requirement related to address beam forming related scenario, right? There is a beam forming, beam tracking, beam switching. So if user is moving, the beam should move along with the user. Uh, After certain extent, if it is moving away from the cell, then the switching should happen properly, right? So there is a beam cell ID which should be reflecting that, okay, after certain level, after certain power level, the change is happening, the switching is happening, or we can call it beam handover. And that's where beam mobility management intelligence has to be there, again controlled by Rig, and then beam forming optimizer. And like performing beam management is okay, but how efficiently you are doing without spending too much of energy. So another application is saving energy with application sitting on Rig with having energy saving related requirements, right? And now all of these different applications built by different vendors, right? And it has to be tested all together on Rig level. So we also have solution to test the Rig as of today, where we will provide all the interface, including entire network, right? You are just testing the Rig. So we are providing you the interface, E2, A1, and O1, O2, which are standard ORAN interface, and your XF and RF sitting here. So the device under test is your Rig, the brain of the ORAN system, and emulating rest of the component from our side, we would be able to offer all testing like we have seen in the end-to-end network before, including providing all these interfaces for Rig testing. So there is more to it, and definitely it's not limited. Rick is just evolving, and we will see a lot of use cases for the framework, which is based on AI ML, training itself, doing verification, and then on top of it, security. So right now we are supporting some of the use cases like I have highlighted related to traffic steering, and we are gonna see more and more use cases. And yeah, you can reach out to our website or any of our like myself or Keshwa, if in case you need more information on our solution and the use cases supported as of today. So that's all I have, but I had another like video demo also, but in interest of saving time, I'm not able to I'm not able to like go through. But if you visit our sparent.com website, there are demo available like for ORU, ODU, OCU testing. So yeah, that's all I have. So thank you everyone.